So now we're going to get back into distribution tables. This time we want to do it with numerical data. So of course we need to define the categories, which is the trickiest part with the numerical data. Okay, and then we'll create the same kind of distribution tables that we did previously for the categorical data. And then also add a couple distributions to that, or just one. Well, sort of a couple. We'll see. Anyway, so we need to determine the number of classes or categories to break the data down into. We need to define the range of each class, or the class interval, or width of the class, same thing, and then the class boundaries. So what's the range of values we can accept in each class? Okay. So there are many different ways of doing this. There's no hard and fast rules. Okay, so but one way is this: sort the raw data into an ordered array to sort the data. So here's an example. Maybe it's some ages in a family get-together or something like that. So we have 20 observations. So the range of the data here is 58 minus 12, right? The max minus the min. That's what defines the range of the data. Good thing to remember. We'll see it again when we do descriptive statistics, because that's one of them. Anyway, so the range is 46. It's 46 observations total, going from 12 to 58. So usually we want to select the number of classes based on the size of the data set. Okay, so we have 20 observations. We don't want to have 20 categories, because that wouldn't be a very useful thing. Right, we want to condense the display into tables and, as you see, charts. So this states if we have too many, like I said, if we have class ranges of 1 or 2, that wouldn't be a very good chart. So this is actually that data. I don't remember what I used here, but I think it's that data. Well, it can't be that data, because there's 60 to 61 here. Anyway, so not a very useful chart, right? One observation on each of these. We got 3 observations here, 2, 1. It actually doesn't look that bad, but we don't. I mean, they're not really good class ranges, right? And then, if we have too few, like with this data, if we made it what, like 10 to 30, and then 30 to 60, we'd end up with something like this. It wouldn't tell you much of anything, right? And these are histograms, so notice no gaps between the bars, and it is a plot of a frequency distribution. So we'll make those in a little bit. So anyway, the whole point of this: make sure you come up with categories that get across good information about the data. Okay, so this is just a recommendation. I stole it out of some textbook years ago. But so if we have less than 50 observations, usually 5 to 7 classes might be good. However, with this data, well, maybe, I don't know, 5, maybe. It would be a maximum of 4. Well, actually, that's not true. I'm thinking even four categories might be okay here. So, like I said, not a hard and fast rule. Oops, where'd it go? 50 to 200. About 7 to 9 classes. Depends on the range of the data too. So it's not just, going by these values, but it's kind of a rough idea of where you might want to start, and then you can adjust as you start working with your data. Okay. And there's also this. I don't know if the OpenStax textbook says anything about this, but it might. I haven't read it that closely. Another way to determine the number of classes is to use this 2 to the k rule. So we choose k, the number of classes, such that 2 to k to the kth power is greater than or equal to the number of observations. Now, I don't care if you use this or not, but you want to come up with something that expresses the data set pretty nicely, clearly, and accurately. Expresses characteristics. So here we have 20 observations, so let's throw 4 into our formula. 2 to the 4th is equal to 16, right? 2 times 2 times 2 times 2, 16. So it's less than 20, so that's not going to be good, at least according to this rule. So what if we make it 5 classes? That's 32. So 5 classes might work well. Again, not a hard and fast rule. You don't have to go by this. It depends on the data. You know, especially if it's in dollar terms, you don't want to have like $1.30 be a minimum and $2.82 be a maximum for the class or something like that. You want to have nice, clear-cut ranges between your category definitions. Okay, so then that's what this is, determining the class interval. Okay, so we have, with that data, that little 20 observation data set here, somewhere there. Okay, so remember we have a range of 46. If we divide that by the number of classes, 5, this gives you a rough idea of the range. So note it says round up. So 9.2, that makes it a 10. So that's a nice even width for it, right? I mean, not exactly 10, because we can't have overlap. But that gives you a nice idea of how to put together your category definitions. Okay, so as I said, they determine the class boundaries. So roughly 10 is the range we want. So the boundaries must be clear with no overlap. Remember, if we have overlap, we can end up with 2 observations, a single observation ending up in 2 classes. Happens to be right on that boundary that's overlapping. So we also want to choose it to make the data easy to ascertain, the information, like I said, characteristics of the data. So we have 5 classes of width 10. So you can either define lower limits or upper limits. And in Excel, it prefers you to define them in a particular way. I think it's upper limits. But we'll see, because we'll do it in Excel. Okay. So here, for this data set here, I'm going to use these as lower limits. So my first range is going to go from 10 to 19.9 to just under 20, right? And then the second range will go from 20 to 29.9. Well, really, I mean, this is nice rounded data, so we can just say 10 to 19, 20 to 29, 30 to 39, 40, 49, 50 to 59. And that covers all of the data. Something you want to check and make sure of. Your boundaries, your categories, once you figure them out, will include all of the data, because that's how we want to make our table. Okay, so that's what I just said, right? Again, you could have just said 10 to 19, 20 to 29, etc. with this nice rounded data. Okay, and then once we have the categories, then it's just doing the same thing we did with the categorical data, right? Just make frequency distribution. So here you can just count them up. This is an ordered array, so pretty easy to do. Right. 4 in the 40 to 49 range. That's where this comes from. And then, of course, we can make a relative frequency and a percent distribution just from that. So pretty straightforward, I hope. So here's comparing that frequency distribution to a stem and leaf display of the same information. So what do you think? Well, they're different, but you kind of see this frequency distribution right in the stem and leaf display. Right? You can kind of see it. Right? We got 6 observations in the 20 to 29 range, and we see that immediately in the table. One thing nice about the stem and leaf display is it's like a histogram. right? If things are spaced correctly or the same, you can view it like a histogram. So easy to see that the 20 to 29 range has the largest number of observations in it. Of course, we see that from the distribution table too. Now, of course, once we get 100 or 1,000 observations, stem and leaf not very useful anymore, unless you can do a real small version. Depends on the range of the data. Okay. And one thing we definitely lose in the frequency distribution is in the stem and leaf display is the actual values of the data points, right? Stem and leaf has the actual data in it. Or if we have to truncate, at least close to the actual data values. Okay, hopefully that makes sense. And of course, you don't get that in the frequency distribution table. And like I said, once we get that, we can calculate relative frequency and percent distributions. Remember, relative frequency is just the frequency divided by sample size. And here, reminder to do the test to make sure you accounted for all your data. Even more important with the numerical, because you might have defined your categories wrong and you might be missing an observation or something. Okay, so let's see. So before we actually go to Excel and make one, a new type of distribution that we didn't do with the categorical because it wouldn't have made sense is this thing called a cumulative distribution. Okay, and this again we make from the frequency distribution, just like we did with the relative frequency and the percent. Okay, and so what we're going to do now, cumulative means we're accumulating everything below an upper bound. Okay, so cumulative distribution states an upper bound and counts the number of observations below that. Okay, and then we can also plot that. Okay, so here's our frequency distribution and the percent. And we'll make a cumulative frequency, a cumulative percent. You could make a cumulative relative frequency. It's the same way. So what's the cumulative frequency of observations in this first class? The class upper bound, under 20. Well, of course, it's 3, or 15%. Okay, what about the second class? How many observations are below that upper bound? 9. Below the upper bound, not including the upper bound. I was counting to make sure I got that right. So there are 9 below. 30 is actually in the 30 but under 40 category, right? So how did I get this 9 or 45%? I just summed up these, right? Everything below this upper bound includes everything in this category and this category. Okay, so do that for the rest. And note that the test here, we don't need to sum these up. That would give you a number you don't need. But if you look at the last value in the cumulative frequency distribution, it is equal to the number of observations, right? All of the observations are less than 60. That's what that's saying. 20 observations, that's how many we have, are less than 60. Okay, or 100%. 100% of observations are below the highest upper bound. Okay, does that make sense? If not, send me a question through the discussion room. I guess that's not sending it. Post me a question. All right, so let's use our raw beer data with templates again. And so we need to define things and make this table. So in the spreadsheet, I already made the category distributions. So it's right here. So we have. So this is again the raw beer data with templates. Not the key yet. I'll post that. later. Well, yeah. So what do we got? So note how I define the classes. I'm actually having the nice round upper bounds because Excel likes that. Okay. So I'm going from $2 and one. I'm looking at beer prices. This is the distribution of beer prices. Okay. Which I think I said in the, yeah. Create a distribution table of beer prices. So I already did some of the work for you. Came up with class boundaries. I made them a range of about $1. Well, technically 99 cents, but you get the idea. And then I put their upper bounds in there, because we'll use these upper bounds for Excel to do the frequency count for us. Okay, so we don't need to sort the data. We could do that and do the count thing to fill in our frequencies, but now we're back to the 69 observations. Kind of a pain. We want to do things quickly. Excel has functions we can use, so let's use them. Okay, so again, once we get the frequency filled in, we can easily calculate the rest of these. So I'll show you some Excel shortcuts. Well, I mean, we can just write Excel functions or math functions in Excel ourselves to fill in tables. But the frequency distribution, we can get Excel to calculate for us. Okay, and we need the upper bounds for that. That's why I threw that in here. Now again, this wouldn't make any sense for the categorical data, because we don't have bounds. We have different categories defined by the name of the category. Okay. Anyway, so in that handout I posted, oops, that's not it. The create frequency distribution. Okay, so last time we looked at this, doing the count with the categorical data. Then we use the count if function in Excel for it to count the number of observations in each category. Now for numerical data, we need to do this. And this is a little different. Okay, this is called an array function. So there's some special things we have to do with it. Okay, so what does it say? Create a frequency distribution table. We have our column headings. Include a class upper bounds column, because that's what Excel is going to work off. Now we want to highlight all cells in the frequency column of the table. Not the header though. Just the cells here from row 2 through row 7. Okay? And then we want to type equals frequency. So I'll just read through this and then we'll do it, because I got to move this off the screen. So this is our function, equals frequency, and then the first thing we put in is the range. Now notice I'm not just selecting the column this time. This will be the beer price data, and I need to actually select the actual data range that will be searched to determine the frequencies. Okay, and then comma, then class upper bounds from the table. So we'll just select M2 through M7. Okay. I mean, ignore the values here. That was when I didn't have a stem and leaf display template in there. Okay, and then closing parentheses, and then this is the tricky part. Hit the Control and the Shift key, hold those down, and then hit the Enter key. That's what you have to do with an array function. If you didn't do that, it would only fill in the first frequency. But we want it to fill in the whole frequency distribution. Okay, so I'm going to move that, and then let's do it. So we have our headers, we have our definitions of the categories, we have our upper bounds, and then we want to choose the cells we want Excel to fill in. Okay, so those are all highlighted. Keep them highlighted. Go up here and type equals frequency. And notice this popped up. You can just double click on it. We'll fill it out. Tells you what you need. Data array we're going to search in, and then the bins array is going to be the upper bounds. Okay, so the data array we're searching in is the price data. and select the actual price data. I don't think that would work with columns if you tried it. You can try it, play around with it, but easy enough just to select the data here. Of course, if we had 1,000,000 observations, that wouldn't be the case. Okay, and then comma, and then we want the upper bounds, right? Data array is where we want to search. Bins array tells it what to search for. In this case, upper bounds. So select all those cells, right? M2 to M7, like I said earlier. And then we can hit closing parentheses. Now don't just hit enter, you need to hit Control, Shift, and then the enter key. Hold down Control and Shift, then hit the enter key. There we go. Then of course do the test. Make sure we accounted for all observations. 69, yes. So we're good, right? If you didn't get it yet, you can always stop, rewind, back up the recording, and try it again. So you should do that. Okay. So once we have the frequency distribution, the rest of this pretty straightforward, right? Same thing we did the other in the previous lecture with the categorical data. Okay, so what's the relative frequency between $2.01 and $3 for the price of beer? There's 7 of the types of beer or brands of beer that are in that range. Out of 69, right? So we want to type a function in there equals the cell reference divided by number of observations. Okay, but remember, we want to make it a constant reference in the denominator and keep it a relative reference in the numerator. Remember I talked about that earlier. We want the numerator to change as we drag this down, but we want the denominator to stay at this cell. Okay, so to do that, you need to hit the F4 key, or function F4, however it works on your machine. Whatever it takes to get a dollar sign on each side. You might notice if you hit F4 more than once, it changes. Oops, I'm hitting the wrong button. Sorry about that. F4 changes that to $1 sign on the right side, $1 sign on the left side, no dollar sign, and back to 2. Well, we want the 2. That makes this a constant reference no matter where you go. The other dollar signs are for dragging it across columns and keeping something the same. Going down rows, I don't think we'll be using that at all. If we do, I'll go into it in more detail, but I don't want to do that right now. Okay, so we got our relative frequency, 10%. It's not really quite 10%, right? Whoops. It's really slightly more than 10% because it's 7 greater than 6.9, so slightly more. Okay, so remember I like my relative frequencies, decimal form of percent out to 4 decimal places. And now we can just fill that down, sum it up. What should it sum to? 1. Remember that? 1. So that's good. And then what about our percent? So we might as well do that before we do the cumulative. So remember, percent is equal to relative frequency times 100. Oops. Or if your cells are formatted as percent, just put equal to that. Sorry about that. So let me redo that here. So this is not formatted as percent. So if I just did that, I would have to multiply it by 100. Or, as I said in the previous video, you can just select this, go hit the percent sign up here, give it 2 decimal places, 10.14. Okay, so I actually already had made this column a percent format. You can right click and format your column. So I'd already set it as percent. change it if you want. And there's all sorts of formatting you can do in Excel. I'm not going to go over a lot of it, but this is kind of an important one. Sometimes you have data that's stored as text, and you might need it as a number to do some calculations. So you might have to check the way it's formatted. But since I made the table for you, you should be good here. So we can just use equals. Note it's a relative reference, so it updated as we move the cell, the formula down. And then, of course, we want to sum that. It should be 100%. Oops. 100%. Cumulative frequency, we won't need that sum, so we'll get rid of it. Okay, so now we have a frequency distribution for beer prices. Prices of 6 packs of beer. The relative frequency distribution, percent distribution. So 20, little more than 20.25% of beers cost between $5.01 and $6 for a 6-pack. Okay. So you should be able to read these tables we're making. About 30%, 30 and a third percent are $4 or less. Right. Note we're including the upper bounds in the cumulative now. So I just made a cumulative for this cumulative percent. But let's go back to so we're going to do a cumulative frequency. So what's cumulative number of beer prices that are $3 or less, right? Because I define my categories with an upper bound instead of defining the lower bound, and this is a better way to do it anyway, especially since it let us have Excel create the frequency distribution, right? But now you have to read the cumulatives a little differently, right? It's not just less than the upper bound, it's actually less than or equal to. And really that's the best definition of a cumulative frequency, as we'll see later when we do cumulative probabilities. Very important concept, we'll make wide use of that. But it's always less than or equal to. Well, at least until we get to the continuous distribution, but we'll hold off on that. Anyway, so what's the frequency of beer prices that are below $3 or less than or equal to $3? Well, of course, that's just the 7. Okay. What about the cumulative frequency below less than or equal to $4? Well, I mean, you could just count them or add them up. 21, right? That would be 21 beers have a price $4 or less for a 6-pack in the status set. Anyway, so you could just do that for each one, or you can make a function. I'm not going to check. You do it however you want, but I'm going to make a function I can have fill in the rest of the column. Okay, so I'm going to have that equal to the previous value plus the amount in that particular category or class. Okay, so there, it's 21, and now that should fill in correctly the rest of that column, and I think it did, because we have 69 observations with prices less than or equal to $8. So all of the beers have prices less than or equal to $8. Now, be very careful. I mean, you may have noticed the way I've been saying things. I say them in specific ways that you need to get used to thinking it. So, like I said, there are 69 beer prices less than or equal to $8. So you'll want to pay attention to how things are worded going forward, because it can trick you if you don't pay attention to it and you misinterpret something. It's pretty important. You got to be careful in your dealings with numbers, and I'm teaching you how to do that. So cumulative percent, same thing, right? So equals first one, 10.14% are less than or equal to $3. And then I'll do the math equation again, equals to that plus that percent. So like I said before, a little over 30%. I said 30 1/3, so I was off a little bit, but whatever. Fill it down, we have 100% of beer prices were under under $8. Sorry, right? All of the beer prices are less than or equal to $8. Forgot the equal sign the first time. Okay, so that's it. We now have a complete distribution table for beer prices for this data set, at least for all the distributions that we defined. I don't have a cumulative relative frequency, but I mean it would just be this in decimals instead of S%. Okay, so hopefully that makes sense. If not, please review. And let's go back to the slides. Well, since I have this key up here, I'm going to show you the stem and leaf now. Okay, so the stem and leaf for the beer prices, or I'm sorry, for the calories, right? Because you were asked to do a stem and leaf for the calories. Here it is. So I'm using the stem as the tens digit. You may have used something else, and that's fine. I bet it doesn't look as good as this, though. So here the 0 doesn't mean there isn't a value there. The 0 means we have a 60, right? That is an observation. 60 calories in this Kingsbury beer. Note, I did sort the data set by the calories to make it easy. Unfortunately, there's no function to make this in Excel. You actually have to do it by hand for a stem and leaf. Anyway, so clearly the category with the most calories, or the most beers in it, is between 140 and 149 calories. Okay. So here we note there are no observations with in the 120 to 129 calorie range. Right? There are no beers in that range in our data set. Here we have two that have 110 calories. In fact, right here, right? Natural Light and Bud Light. Node 190 calories. There is one that has 201 calories. Right down here at the bottom, highest calorie beer, Elk Mountain Amber. Never had that. I think I've heard of it. This Old Detroit Amber, I never even heard of that one. Anyway, beside the point. So anyway, so that's what you should have gotten, unless you use like a ones digit or yeah, I mean you could have used the ones digit for the stem. No, you couldn't have. That wouldn't have made any sense. That would be garbage. That would just be your data. Well, what about the hundreds unit? Yeah, then you'd have 0, and all of these would be to the left of it, and you'd have to truncate. So really, this is the best stem and leaf. So hopefully you came up with this one. If not, you might try it again and see if you can. So you could also do a stem and leaf with the price data, or alcohol content, or anything else. Okay. Okay, so this we just did. I forgot I had this in the slides, but showed you how to do everything. But if we use the calculations I previously had talked about, so we have 69 observations. The range went from $2.36 to $7.80, which is 5.44. Range of $5.44. So I used 6 classes for that. I rounded this up, got to 6 classes, and each one, so taking the 544 range divided by 6 gave me a range of about $1. And that's exactly what we did, right? Now, why did we use 6 classes? Well, worked well with the range. But you don't have to go by that. That's not a hard and fast rule. Remember, it might make sense to break it into more, or maybe one fewer. But in this case, it worked quite nicely, right? We made it roughly $1, really a 99% width, class or class range. So that's what we did. And I'd already done that for you. This we did. This is what's on that worksheet, the Create Frequency Distributions worksheet. Oh, I guess you can select the whole column in this case. I wasn't sure, and I didn't want to waste time in case it didn't work, because some functions don't let you do that, which is really annoying. But it's very nice when you can do it, except make sure there's nothing else in the columns. You might have done some calculations under your table or something. This happens to me sometimes. And then that gets counted in your data, and it shouldn't be. So be careful about that. Anyway, so this is everything we did when we created that distribution table. And this is what we came up with, right? Okay, so this I didn't have in there before, and you know what? You don't have to bother. I'm not going to... I'll show you why it's there. It's just for a particular kind of graph. I don't even think it's that good of a graph type. So you don't need to worry about it. But we will make use of it in the rest of the presentation here. Okay, so keep this handy. We're going to make some pictures. Okay, so I'm going to stop this video here before we make the pictures. Okay? And that will be a separate video.